Welcome back to the channel, guys. Today we are continuing the very last chapter in the book. And this one is kind of a special one in that there's really not too many numbers as far as calculations involved. There's obviously numbers, but today we're going to be looking at more types of data displays. And specifically today, you can see the title, Shapes of Distributions. So today we're going to be looking a lot at histograms. If you forgot what a histogram is, this is what they look like. So I'm adjusting my camera there. Sorry about that. Histograms are a great way to show kind of how data are spread out. And today we're going to look at those shapes. It's typically going to be histograms. It doesn't have to be because the shape of the data can give you a bit of information about the actual data itself. And that's what we're going to get asked about today in the questions. So today there are three basic types of shapes of distributions. Probably the most common, I don't want to say the common, but the most popular one is this on the left, right? You can see what I have here. I have three different histograms. Basically, I just made up some data about the number of tardies that students had, and then this has frequency. It's kind of hard to see. So I've got 1, 2, 3, 4, 5, 6. So like, for example, in this graph, one person had between 0 and 3 tardies. This is 4 to 6. We have 3 people. The frequency of there is 3. 3 people had 4 to 6 tardies. The highest bar here is at 5. 5 people, 5 students had between 7 and 9 tardies. Down here again, we're at 3. So 3 people had between 10 and 12 tardies. That's what that number is, or that interval is, if you can't tell. And then the final interval, because histograms always have intervals, 13 to 15, we only have one person, and you can probably guess who that might be if this was real data. One person had between 13 and 15 tardies. So anyway, whenever the general shape of the curve, these are typically called like a bell curve. If you ever heard a teacher say, hey, I'm going to grade on the curve, this is kind of where that phrase came from. Anytime you can kind of see, and I don't want to put my hand on the board here and mess up the writing I have, when it's kind of just a very symmetrical display like that, you have a symmetric or bell-shaped graph or a distribution, right? This is the most common one whenever it's kind of symmetrical, right? It's almost like I could draw a line of symmetry down the middle and the right-hand side matches up with the left-hand side. Now, it doesn't have to match perfectly. Now, mine matches perfectly, but it doesn't have to be that way. As long as it's generally symmetric like this, we're going to call it a symmetric shape. And what can you figure out about a group of data whenever it is symmetric? If someone asks you which measure of center is best to describe this type of a graph, you want to use the mean, because the mean is usually right here in the middle. And if you have the same amount on the right as you have the same amount on the left, the mean's going to be somewhere in the middle. And so the mean is going to be the best indicator to describe this data. So if we're talking about the measures of center, you'll pick the mean. If they're talking about the measures of variability, you'll pick standard deviation. And so we're going to get some questions today where it's going to ask you, hey, which measure of center would be best to describe this data? And so if it's symmetric, you're going to use the mean. And if it's symmetric, you're going to use standard deviation, mean and standard deviation, right? Remember, this is a measure of center. This is a measure of variability from the last lesson that we had yesterday. Okay, that is the most common one, symmetric. But data doesn't always look like that. Sometimes you'll get it either really, really weighed heavily on one side, or maybe all the bars will be stacked up on the other side. And so that's what we're going to look at on these other two. The second, I don't know why my board keeps sliding here. Hang on, guys. I don't know if I got it off center or what, but it just keeps sliding on me. It's kind of annoying. Okay, I think I got it fixed now. There are two other types, because it won't always be perfectly symmetrical like that, right? Sometimes you'll get something like this. You see how the tallest bar here is way on the right-hand side, right? We've got the tallest bar way on the right, and then we've got this long tail, right? If I drew my kind of curve, look how this one's going to look. It's going to go, and it's going to go down that way. It's not as perfectly symmetrical as this one, right? This is what we call skewed left, right? You've got this long tail over here on the left, skewed left, and this is kind of confusing to me the first time I learned it, because I'm like, well, wait, look, the tallest bar is right here, and the tallest bar is actually kind of on the right-hand side. But it's kind of backwards from the way that it would make me think in my head. All right, skewed left actually means, skewed left means most of the data is on the right, right? If we have most of the data on the right, we call it skewed left, which seems kind of backwards to me, but that's what they call it. To be honest, I think it's called skewed left because you get this long tail, this long kind of diagonal line kind of sloping down on the left-hand side. So whenever you see the tallest bar and you see it's really, really heavily weighed on the right-hand side of the center, that's when you know it's going to be called skewed left, right? Most of the data, especially the tallest bar, most of the data is on the right, so we're going to call it skewed left. So it's kind of flip-flopped from where the tallest bar is. But I think it's more talking about this. It's kind of skewed because you got this big, long kind of curve on the left-hand side, and on the right-hand side, it just kind of falls straight off the cliff, right? So that's going to be one of the examples where it's not symmetrical. The other example will be the complete opposite, right? Look at my very last one. On this one, if I drew my little curve, it goes like straight up here, and then it kind of gradually wears itself down over there. So it's almost like the ski slope, so to speak, is on the right-hand side. The tallest bar here, right? You see the tallest bar is this one, and that's on the left-hand side of the data, right? So this is the complete opposite. Here you have the tallest bar on the left. Most of the data is on the left, and you're going to call it skewed right because you've got kind of this long slope going to the right. And so the name, I think, comes more from the kind of the long sloping little bell curve you get more so than the tallest bar. Because when data is, let me write this in here, most data is on the left. I'm just going to put left because I don't have room for it, right? Most of the data is on the left. You call it skewed to the right, right? Our tallest bar is on the left. We've got this long kind of sloping, almost looks like a skateboard ramp going down to the right. That's why it's called skewed to the right. Most of the data is on the left, and that makes it have this hill, this kind of slope going down to the right. So that's the opposite of this one, right? Here we had the tallest bar on the right, and we have this long slope going to the left. So this one's called skewed left. It's almost like you could skateboard down the left-hand side here, right? I wouldn't want to skateboard down these steep slopes. That would cause me to get scared. So anyway, here is skewed left. Skewed left looks like this. Skewed right looks like this. And if I asked you to pick a measurement to describe this data, I would not want to use the mean because the mean is going to get messed up when it's not symmetrical like this. Look what they have. Whether it's skewed to the left or skewed to the right, both of these, it says use the median to describe it. Use the median to describe it. The median will be closer to most of the other numbers in the list. And then also, I don't want to use standard deviation. You can see that it says use this 5-number summary. And if you watch my previous video, you remember, I hope, what the 5-number summary is. The 5-number summary is, remember when you did a box and whisker plot, the 5-number summary was the low extreme, the low quartile, the median, the upper quartile, and then the upper extreme, right? Those are the 5 numbers. The 5 numbers that you use to make your box and whisker plot, right? The 5 dots, 1, 2, 3, 4, 5. Those numbers might be much better to describe this data, to describe the variability of this data than the standard deviation. Standard deviation doesn't work very well whenever it's skewed one way or the other. Okay, that was a lot of talking. I'm almost at 10 minutes, but those kind of terms are definitely going to help you in a lot of questions today, right? Symmetric. It's very balanced on both sides. When it's symmetric, the median, and the mean are both kind of perfectly in the middle. And so pick the mean to describe the measure of center. Use standard deviation to describe its variability when it's symmetric. Whenever you get a bar way on the right hand, the tallest bar is kind of on the right-hand side, and you get this long tail going down to the left. When most of the data is on the right, You call it skewed left because you get this long slope on the left. When data is skewed to the left, the median is the better descriptor, and the 5-number summary shows you the variation a little bit better, the variability. And same thing over here. When the tallest bar is on the left-hand side, you get this slope going to the right. That's why it's called skewed right. Most of the data is on the left. The tallest bar is on the left. Most of the data is on the left, so it's called skewed to the right. You get this slope going to the right. When it's skewed to the right, you still use the median to describe it, and you still use the 5-number summary. Okay. All right. Let's go to the next board. Here's why. This is in our book as well. Oh, there was one other type. You might have been thinking there, well, hey, what about if all the bars are about the same height, right? Now, I didn't label this with number of tardies or anything, but here would be one other type. I don't think you'll see this in any questions. If all the bars are the same, or they don't even have to be exactly the same, maybe one of them is just like a little bit higher, something like this, and then maybe this one down here is just a little bit lower or something. But if they're all just kind of relatively the same height, or they are all exactly the same height, if it's like completely flat, we won't call it it's still symmetric, but it's not going to be called just symmetric. We would call it uniform, right? If everyone's wearing uniforms, we all look the same, or flat. Call it flat or uniform. It is symmetrical because the right-hand side kind of matches the left-hand side, but this is a different type of symmetrical. This is called flat or uniform. I don't think you'll ever see that, though, in today's questions. So anyway, let me get that out of there. This is kind of neat. This was in our book as well. If you have your book at home with you, this chart is in there. When data is symmetric, we want to use the mean because the median is right in the middle here. The mean will be in this bar, right? If this bar represents, the numbers 7 through 9, I would say, yeah, the mean is probably 8, right? The mean is probably in the middle of 7 through 9. When data gets skewed to the left, you see here how the tallest bar is on the right-hand side, and we've got this long slope kind of sloping down to the left, and here it just kind of goes straight down. When data is skewed to the left, look where the mean and the median are, right? It's not in the middle like we had before. The median is the better descriptor. I just said that on the last board, right? Whenever it's skewed, you want to use the median because the median is still kind of in the middle, right? The median is somewhere in this bar usually. It's usually closest to the highest bar is right here. It's usually the one right next to it. And then 2 bars away from it is usually where the mean is. And so that's why we don't really use the mean when the data is skewed, because the mean is kind of pushed further away from the highest bar. And so that's why it said pick the median whenever we're dealing with data that's skewed to the left, or for that matter, when it's skewed to the right. Oh, geez, looks like my fingerprints got on here and messed up down there. Sorry about that. So like here, you've got straight up, and then here we have a gradual slope going down to the right. Our tallest bar is this guy right here, isn't it? So we've got most of the data are on the left. Our tallest bar is here on the left. Most of the data are living over here on the left. And so since that's where most of the data are, the median is going to be in the bar next to it. And that's why the median is the better descriptor, because most of the data is over here, and the median is close. It's not perfectly in that bar anymore, but it's in the bar next to it. Like if this bar was maybe maybe this is like 4 to 6, I would say, yeah, the median's probably 5, right? And then if this category was like 7 to 9, I would say the mean is maybe 8, right? But the mean is further away. Like most of the data is right here. The median is right next to it, and so that's why we picked that. The mean is 2 bars away, and so we really don't want to use the mean to describe either one of them that are skewed, just because it's further away from most of the data. Most of the data is right there. I want to pick the median because the median is still right next to it. So that's kind of how it works. So it's going to ask you maybe which one to use, right? Should I use the mean or the median to describe this data? And just kind of look at it. If it's symmetric, pick the mean. It's going to be in the middle. To be honest, the median would also be in the middle, but the mean is better. Here, when it's skewed to the left, pick the median because it's only 1 bar away. When it's skewed to the right, same thing. The median is only 1 bar away from that highest bar, typically, and that's the one you'll use there. Okay, we are getting close to the end. I only have 2 more. There's really not any questions today. More so the questions you're going to get in the book, it's going to ask you to describe histograms. And so you're just going to be using all the information on these boards. There's really not a lot of actually solving things that we're going to do. Okay, one thing that's really cool about the symmetric graphs, right? The ones that look like this. Whoa. The ones that have that bell shape. Here is just a bigger version of the one I showed you at the beginning of the video, where I did number of tardies, 0 to 2, 3 to 5. You can see 6 to 8 tardies, 9 to 11. Histograms always have to have intervals like this, 12 to 14, 15 to 17, 18 to 20, right? So that's how many tardies students have over the course of the year, I'm assuming. And then I have the number of students, or they usually call that the frequency. So you can see we have 2 kids who had no tardies all the way up to 2 tardies. Our highest bar is right in the middle, 9 to 11 kids, or 9 to 11 tardies. We've got 7 students who had 9 to 11 tardies, right? And you can kind of see how it looks. So one thing that's really neat about symmetric graphs, because they are used a whole bunch in statistics. They are used so much all over, not just in a math class. These are used well, in almost everything. Anyone who does statistics, not just for a school or an education or for a university or college class, statistics are used quite a bit. And people use standard deviation a lot, right? So one thing that's really cool, if you have a symmetric graph, something that's like this, very symmetric, you know you're going to use the mean and you're going to use the standard deviation to describe it, but you can also get even more detailed than that. Right? So let's say, because like here's our tallest bar, obviously, and it's in the category of 9 to 11. So I just assume that the mean is probably 10, right? Because that's halfway in between 9 and 11. The tallest bar was right here. And so I'd say the mean is probably 10. And then the standard deviation, if I actually had all the numbers, I could calculate it. We're just going to say for the purpose of this example that the standard deviation is 4. Okay? So they are telling me this information. I could have calculated it on my own. In real life, people calculate that on their own all the time, or they have a computer program that can do it. And then here's some cool facts. Let me scoot my thing over here so you can see it. And this is super interesting. I had forgotten that I'd learned this way back in college. And this is true for any data, not just my little example I made, but in general, any data, no matter what you're doing, about 68% of data will lie within 1 standard deviation of the mean. And then about 95% of data will be within 2 standard deviations of the mean. So let me show you what that means. All right? So you see up here where I said the mean was 10, and then the standard deviation was 4. So if I said 68% of the data are within 1 standard deviation. So if the mean is 10, right? If I said, okay, the standard deviation is 4, that would give me all the numbers that are 4 above and 4 below the number 10, right? So we could say anywhere from 10 plus 4, 14, or all the way down to 10 minus 4, which is 6, right? So this would be like the low, and this would be the high limit here. So if we go 4 above that number or 4 below that number, from 6 to 14, we should have 68% of our students. 68% of our students are in this category from 6 to 14, right? And you can see, look, 6 would be right here. That would be this bar. That would be 14, goes all the way up to here. That's 12 to 14. So 68% of our students will be within 1 standard deviation of the mean. They'll either be up to 1 standard deviation above 10 plus 4, all the way up to 14, or they would be 10 minus 4, as low as 6, right? So 68% of the people on average, right? Usually it's about 68%. It's not always 68%, but it's usually close to 68% of your data, of your individuals, of the people, the students in this case, would have between 6 to 14 tardies, right? So 68% of our students, like if I was Ms. Brown, Mr. Tobin, trying to figure out about how many tardies do students get in our school, and I needed to report that, I could say, hey, we've got 68% of our students that have between 6 and 14 tardies. And then why does this person have 20, right? Fact number 2, let me actually hit that before I move on. about 95%, let me scoot it over, 95% of the data are within 2 standard deviations, right? So if the standard deviation, if our mean is 10, and then one standard deviation was 4, and we could say 4 above, we're also going to do it twice, right? So 2 standard deviations would be 4 plus 4. So if I include this all the way up to 18, and then if I do it the other way, if my mean is 10 and the standard deviation is 4, if I go 2 standard deviations below, it's going to be 10 minus 4, which is 6. 6 minus 4, which is 2, right? So I would say 95% of our students have between 2 and 18 tardies, right? So if I go to 2, which on my graph is, well, 2 would be like kind of included in this bar, but 2 would get all of this. It would get all the way up to 18, would get all of this, right? And so now you've got 95% of our students that are within these categories, right? So if I was talking to a student that was way up here, and I could say, hey, 95% of the school has between 3 tardies or 2 tardies and 18 tardies. Why are you sitting over here with 19 or 20? And then they use this type of data all the time whenever they are trying to qualify people for certain types of tests, right? To see if you qualify to maybe make it into a certain advanced level class or a class where you're trying to be compared to people around you, right? They want to find the best of the best, or maybe people on the other end, people who really, really need help. They use standard deviation all the time to figure out where most people are and then where you are, right? And so we could actually, if I wanted to, I'm not going to take the time to do it, we could actually count, right? We could say, oh, there's 4 students here, this bar is at 6, this bar is at 7, this bar is at 6, this bar is at 4, these bars were at 2, right? I could actually calculate, was it actually about 68% on our data? I don't know. I could say 6 plus 7 plus 6, that's, I could add those up and get 19. I could say, hey, 19 students out of my total here, which I think my total is 31. So I could say, yeah, 19 out of 31, and then I could divide 19 by 31 and see how close it is to 68%. If I just clear this out, 19 divided by 31. Whoops, I hit an extra button there. Now on mine it's 61% because I just made these up. This isn't like a real group of numbers. And then you could actually figure out if this other category is close to 95%. So that was really cool, I thought. And another way you'll see people describe it is they'll say this, all right, okay, so the mean is right here, right? The mean was 10. That was our mean. The mean is right in this bar. And so they'll say, hey, from here to here, right, this is plus 1 standard deviation. This is minus 1 standard deviation. From here to here, it represents 68% of your people. And then you can even extend it for this last category. If I do it all the way, let me kind of draw this down, from here to here, kind of match that up. See how it kind of matches up right there? Where now you're not just 1 standard deviation away, you're 2, you've got 1 and then 1 more here, or you're 2 to the left, this is the standard deviation symbol, you should say 95% of the people are in here, right? And that's 95%. So I don't know if they'll ask you about that in today's questions. I just thought that was cool, and so I put it in there. Okay, very grand finale. Today, all we've looked at is histograms, but it doesn't have to be histograms, right? It could be a stem and leaf plot. Stem and leaf plots can have shapes to them as well. So we're going to have, I think, 2 questions today in the group of questions I give you on our Big Ideas Math website, where it asks you, hey guys, describe the shape of this data. And whoa, this is, I just made it up, basketball jersey numbers, right? I just made up some random jersey numbers. And then here's another one, the book numbers for my algebra class. And you can see, look at this one, how this one is much more symmetrical, right? I would call this one symmetric, right? When it's symmetric, what would I use to describe it? I'm going to use the mean to describe this. I'm going to use standard deviation to describe the variation of it. Over here, you can see, whoa, look at that. That is not symmetrical, is it? We've got most of our numbers are in this category and in this category, right? And if I turn this board kind of sideways up here like this, you can see how most of the data are on the left, right? Most of my highest bars here are on the left-hand side, and then it skews down. It kind of slopes down. So this is definitely not symmetric. This is one where I would call it skewed to the right, right? Most of the data, remember if I flip it up here, most of the data is on the left, so I'm going to call it skewed to the right. And whenever it's skewed to the right, I don't want to use the mean to describe it. On this one, I would use the median to describe it. And then I would also use the 5-number summary to describe the variability. Okay, so I think that's it. I'm going to stop right here. Thank you so much for watching. I'm going to put this on the Big Ideas Math site. There won't be too many questions today, but use those boards that I had at the beginning of the video. Feel free to pause the video so you've got that up where you can see it and use it on the questions. Thank you so much, and I'll catch you guys in the next one.